Uh, yes, I've started the recording. Yeah.
Achan, please start the prayer, Achan.
Okay. Let us look to God in prayer. A merciful Heavenly Father, thank you for this beautiful afternoon. Thank you for giving us yet another opportunity to gather before you in this platform to deepen our understanding and expand our knowledge. Lord, thank you for giving us the opportunity to get introduced to new avenues and to new areas of knowledge. Gracious God, especially we pray for our management, the provisions that we are receiving through this institution. Gracious God, help us to utilize it in the right way so that we are enriched and also our students are also blessed with that. Lord, as we read in the Bible that the fear of Lord is the beginning of wisdom. Lord, grant us the wisdom and knowledge and give us the capacity to grasp the knowledge that is disseminated. We pray for our leaders who are committedly serving and leading these sessions. Lord, continuously from the beginning till today, in every session, your guidance was there. Things has went in the perfect way. In everything, you have guided us, Lord. Once again, we submit today's lecture and all the series which is about to happen in the coming days also. May your grace wound us and protect us and guide us. We submit each and everyone into your mighty hands. Especially, we submit the leaders who are leading today. We ask this prayer in the name of our Lord and Savior Jesus Christ. Amen. Thank you so much.
Thank you, Achan. Thank you for the wonderful prayer. Anand, sir, please share your screen and start the meeting.
Sure, sir. So thank you, Professor. Thank you, Achin, for the prayers. So let me share my screen and start sharing the slides. Yeah, so good afternoon, everyone. So we have a very low attendance today, but so those of you who have joined, so I hope the session would be of some use to you with respect to Simulink. So we would be covering the topic system level design with Simulink. So how you can use Simulink in multiple ways in multiple domains, both in your teaching activities and research activities. And with me, Shovik will join soon in maybe around 3:15 or so. So he would be also taking some of the portion in the second half, and I will be starting off with the session. And for any queries, means even after the session, I know you are having academic activities, you may have doubts at a later stage. So you can contact any of us, whether it's related to licensing, whether it's related to technical doubts, or anything that comes up to your mind, whether it is related to support. So we have an extended support team also, or training. You can just let us know. We can address the queries, or forward you to the right team. Yeah. So today's agenda is like this. So we will have a brief introduction of what Simulink is all about and what are the different capabilities, and what do we mean understand by the term model based design. So this is a well known term where whoever is working with Simulink will know this word. And then we will go through some demos and give an overview of different modeling capabilities of Matlab, Simulink, and Simscape, followed by a question and answer session. Right. So, so in the last couple of sessions, we have totally focused on the MATLAB software. Sorry, how we can use it. So by this time you must have understood that it is a very user-friendly kind of technical computing environment where you have lots of inbuilt functions and apps and other libraries, and the syntax and which is filled with documentation. So that is a very key aspect. So even if you want to do something but you're not sure about it, if you type those terms plus MATLAB or plus MathWorks, then you will get some links which will lead you to some page, documentation page, and you can get started with those, whether it's related to mathematics, whether it's related to some of your engineering or science subjects. So most of them would be covered. So that is another one thing. And Simulink is nothing different. It is just a part of MATLAB. Only thing is that here we have a block diagram based environment. So you will have a blank template where you have to uh, make make your system using predefined blocks. So there is a library from which you can choose those blocks and make appropriate connections, give the settings correctly for model-based design, and it also supports multi-domain simulations. So by multi-domain, uh, uh, what is the meaning of multi-domain here? Multi-domain means it can not only model blocks or systems related to one particular discipline, for instance, electrical. It can simulate blocks from multiple disciplines like electrical or mechanical or fluids. And one of the sub branch of Simulink is Simscape, where we can do actually club all these three different physical components, physical bodies or physical domains all together. So there are ways to do that as well, and especially for embedded engineering systems. So wherever there is some kind of deployment involved onto some embedded hardware, so Simulink comes into the picture because it is a very powerful testing environment. So even before deploying, uh, even was there a question? I just heard something. So was there a question or? Okay, and you can type your question also throughout the session in the chat window. So we will try to look over that as well. Yeah. So yeah, let me continue with the presentation. So whenever we want to deploy our design, so into some target hardware, which could be low-cost Arduino device or Raspberry Pi board. Okay, so for that we need some specific code which is required, which is compatible to that hardware. So once the design is ready, you can automatically generate the code before deployment. And even before that, you can actually test the system. So test it extensively whether it is giving appropriate results prior to deployment. So that is the main advantage here. And these are the different sectors where Simulink is used. Mainly, it is used in wherever there is a need of controlling or control systems. So, for instance, in aerospace or automotive, so lot of controlling is required. Whether you are controlling a part of engine or you are controlling some aspects of different uh, devices present in the entire system. So all those control modules are heavily relied on these kind of computer software, where we need to actually test it in the simulation environment prior to deployment. And likewise, there are other industries as well, where uh, there is use of Simulink for such scenarios. But most importantly, aerospace and automotive are heavily using these things. So now this is the slide where you can see this blue origin. So this is the company which is sending uh, space shuttles into the orbit. So we are also this is one of the top companies on aerospace, and uh, they too use Simulink for the designing some of the systems. So that is a great thing. And as I mentioned before, that uh, all of the top 10 auto manufacturers as well as all of the top 10 aerospace companies, they rely on Simulink. That is the reason in industry. So in industry sector, these sectors they heavily use it. Apart from that, we also have three of the top 5 internet companies who are using Simulink as a software. So what is model-based design? Now we need to understand that. So let's try to look at a conventional method of building a product. We are talking about systems, but what are the steps, the conventional steps required to build a product? So let's go through that. So whenever we need to design a system, so we need to understand the problem statement and the requirements. So we need to define those requirements. What are the design objectives and what are the constraints involved in that? So that is the first step. So once we know that, then we have to identify for that system what are the different physical components required, whether it's a purely mechanical system or a purely electrical system or a control system or a combination of all three, requiring an embedded software as well. If it has to be deployed in some embedded hardware, so it may need all four of these components. So that has to be understood. So and the problem has to be subdivided. Okay, electrical control and uh, software, and finally it has to be integrated all together. So this is known as system integration. So the sub modules are created, we have to integrate and test it, and only after proper test results we can finally deploy it, uh, uh, or deploy the system or make the system into a actual hardware. So obviously there are multiple things here. So whenever we are talking about the system, so first of all, in the first stage, it is difficult to analyze or very easy to misinterpret. So understanding the problem statement itself is a challenge. So you need to understand it correctly. So the more clearer you are in the first step, the easier it will become in the later steps. Otherwise, you have to again come back and redefine the problem. So it is very important. And then it is also difficult to integrate with design. Okay, so when there are multiple aspects involved, so if it is a purely mechanical system, then someone with a background of mechanical engineering can work with concepts they have learned and build a system. But suppose it has a mix of multiple disciplines like mechanical and electrical and control. So in that case, they have to, the team has to be proficient enough, or there has to be some kind of collaborative work. So either someone is doing the mechanical system, someone is doing the electrical system, and at the end, when they're integrating, they are able to integrate it all together. So there is some difficulty there itself, and also there is difficulty to manage as they change. So it may obviously once you're designing something, you have some statements, some requirements. So these requirements may also change, so with respect to time. So after some time, maybe the person who has given these statements requirements may change it slightly. So you have to be careful or thoughtful about that. As if the change means based on that change, that will also affect, that can actually affect the design quite drastically. A minor change can drastically change or drastically increase the effort that is required again to go through these steps. So these are the common challenges. Next, with respect to physical prototypes, so to buy these components, the physical components, so these are expensive. Some of the components will be expensive. Some you may not find in the market, so it can be incomplete as well as expensive, and it will prevent rapid iteration. So if you want to build the design and then move ahead, then it will be not only time consuming, but it will be a very tedious process, means building the components and testing it again and again. So that is a very challenging thing to do actually. So if we are not clear about if the design is new, we are not knowing whether this will work or not. So building the things all together and testing it, so this will be a this will need multiple iterations. So it will become obviously difficult. And similarly, the manual coding aspect. So once you have designed your system, so and you have to put the system into some embedded in the form of embedded software into some embedded device. So you need to understand or translate that design into that particular coding style. So that itself is time consuming. So if that can be avoided, that is another good thing is how we can reduce this manual coding time, and uh, which is reliable also. Means the coding should also be reliable. It is not that it is just generating a code which may not work. It could work better than the manual coding thing. So these are the things to consider. And then coming to traditional testing. So in traditional testing, the first point which is mentioned here, which is design and integration issues are found late, okay, and difficult to feed insights back into the design process, and no traceability. So this is a very common thing in industry. So if once the design is made completely, so you cannot simply sell it or terminate a product which is ready to be uh, placed in the market, but you have to test or do test trials, and during those testing actually you will find multiple errors which needs to be resolved before actually sending it as a product. So that tracing the error will become challenging once the entire system is made. So maybe you are able to see the error, but what is the cause of that error? To detect that becomes a very challenging task. It can in any of the stages from the beginning itself. Okay, whether there is some error uh, in the mechanical part or in the control part or in some misinterpretation from the problem statement to the design stage. So it can be the cause can be anything. So understand that itself is challenging, and once you understand that, you have to again go back and go through these steps, and again you have to check where you may find some other problem. So this overall procedure is quite challenging and tedious. So that is why the requirement errors are most expensive to fix during testing. Okay, now in this graph you will be able to see what are the different phases of a project. Okay, so first requirement phase, where we are listing down the requirements of a project or requirements of a system that is to be made. Okay, so suppose we have this amount of error. In the requirement phase, we are able to identify what are the different errors introduced in it, and this is range of the relative cost to fix that error in the first stage itself. Okay. Now, if we go to the next stage, which is known as design phase, right? So in the design phase, so we will have two kinds of errors now. Not only the errors in this particular design phase, but the pre errors. Okay, so which may mitigate to this phase as well. Now we have to fix both the errors. Now, if we see here, so the amount of time or amount of cost required to solve those requirement phase errors is much more compared to the errors which are arising in that particular phase. Okay. Similarly, if we go to the next stage, the previous stages, the cost to fix it again increases. Okay, both in the requirement as well as in the design phase compared to the current coding phase. And finally, once we have made the system and we are testing it, so during that phase, this is the range of difference you can see in to fix the errors in the requirement phase. Okay, so it is like an exponential rise. Okay, so if you not solve or do not do not diminish the errors in the requirement phase, it will mitigate and it will create this much trouble in the later phases. Okay, so each and every phase has to be dealt very carefully while we are moving to the next stage. Otherwise, we will have errors, but the cause of the error will be due to the previous stages, and it will take a lot of time. And from here, you can understand that the requirement errors are the most expensive to fix during testing. So once we are testing it, so the most challenging thing is to, or the most difficult thing is to solve the requirements. It will take a lot of time and effort. Now, how model-based design can help in preventing this? So in case of model-based design, you are able to save time by developing in a single simulation environment, and okay, so yeah, so so by model-based design, what we mean here is that so you are actually not making system, but simulating the entire system inside the software. Okay, so here correcting those errors is much easier compared to correcting the errors while designing your system. So that is the concept here. So once you have made those system which need different components and different aspects or physical components, and simulated the entire system, so you can iterate it multiple times in the simulation software itself, and it is giving good performance, then you go for the deployment aspect. So that is the main concept here of model-based design. So simulating it earlier and then use those low-cost hardware prototypes, which will help you give the error, help you to detect those errors via continuous simulation. So you have to simulate it multiple times prior to development of hardware, and it will be a easy integration process. So now what we will do is that, one second. Yeah, sorry about that. Yeah, so now coming to some of the examples in industry. So this is Aurora Centaur. So this is an autonomous aircraft, and they have used model-based design with Matlab and Simulink to develop their flight control. Okay, flight control for flight controller for the flight management software. So they had many challenges like modeling the aerodynamics or the propulsion systems, the electrical systems and flight controls. So for that they used the model-based design approach for integrating all the aspects or to build a successful prototype. Okay, and this is you can understand that this is very important because building a prototype for an aeroplane is obviously very expensive. So you cannot just build a prototype before rigorous testing. So that is here, and they could do that using Matlab and Simulink. So there is a small video clipping of how the controller is able to operate properly for controlling this flight. Okay, so you see there is the controller is actually operating it. There is no one inside, right? So this is a pilotless flight of Aurora Centaur. So that is the challenge that they were able to mitigate. So designing a controller which can fly a flight and also land it properly. Now coming to another user story. So here we have this Aether Energy, which develops an electrical two-wheel scooter, and it also has charging stations, and they have used model-based design approach again. So here the main thing is that it is their first intelligent electric scooter, and where they have used the MBD approach, so to simulate and optimize the scooter design and to generate production code for its control software. Okay, so you see the term control again. So the software which is controlling the scooter, so to generate the production code for that embedded hardware, they have designed the model-based design the system using the MBD approach. And what were the results here? So the design alternatives evaluated in weeks and not months. So time is reduced by 50%, the testing time is reduced by 15%, and field issues rapidly resolved. So even after sending a prototype, there may be some field issues, but most of the issues could be solved in simulation mode. So that is the reason they could able to solve it properly. Now, so why were these industries successful? So benefits of continuous testing and verification. So this is again a similar workflow that I previous slide I covered in the previous slide. So first is the requirement phase, then is the design phase, then is the implementation, and then is the integration phase. The only thing here is that here we have these sub modules, what things that are happening inside each phases, and all the phases are have a common which is known as test and verification. So after the first phase or second phase, third phase, fourth phase, we have to test, verify, and find those errors. If the errors are from the previous stage, we have to go back, and this is how we have to keep on iterating it before the final deployment. Okay. So we have domain specific details added to refine the model, and intellectual property and engineering data reused from existing designs and CAD tools, okay, computer-aided engineering tools. So in this design phase, as you can see, we have the different environment models, different physical components and algorithms involved. So we need to design those sub-modules, whether it is related to mechanical or electrical or controls or some other domain. We need to design it, and whatever algorithms are required, we need to combine it all together. Okay, so this is a very important stage, the second stage, the design stage. And then coming to the implementation stage. So when we are implementing it, when we have the design ready, so we have to understand what kind of hardware is needed. So where it can be a microcontroller unit, a DSP processor, FPGA or ASIC device, or any analog hardware. So each of the different hardwares are compatible with different kind of codes, like microcontroller and DSP are compatible with C++, FPGA and ASIC are compatible with the HDL, VHDL or Verilog code. Similarly, analog hardware have SPICE-based coding. So system, the block diagram based system has to be converted to that thing. Then we can deploy it into the hardware and again do the integration part. So this saves a lot of time in manual coding as well. So again, in this phase also we are we have less effort than manual coding, because it is done mostly by the tool, and there are fewer errors in this in the workflow as well. And even if there are after this stage, after the implementation stage, we can always go back and read the process, okay, just by changing some of the blocks after finding those errors, and again rerunning the code generation phase and integrating it again. So overall, it will save a lot of time for test verification as well. Okay, so these are the general benefit of this continuous testing and verification. So now I will start with some simple demo, and I see Shobik has also joined. So after a while, I will also tell him to cover some of the demos related to Simulink to get started. So this is a basic session. Let me open the Matlab window. Okay. Calculus blocks. Yeah, let me open this one. Okay, so I hope my Matlab window is visible to all.
Yes, sir. Visible.
Okay, thank you, sir. So this is an example to show how we can use Simulink to come to some simple mathematical operations like differentiation or integration. So this is a Simulink environment where you can actually, so let me just show you from the Matlab window itself. So inside the Matlab window, we have this Simulink block. So if we go here, another dialog box will open up, from where we can create a blank model, or there are some specific block sets or toolboxes related to those domains. So we can start with those as well. But for now, let me just show you. If you open a blank model, you will get a blank template kind of thing, and you have this library browser. So inside the library browser, you have multiple sections like Simulink or similar to that that was shown earlier, like aerospace block sets. So blocks related to aerospace would be found here. Blocks related to DSP would be found here. Okay, so similarly, it is divided. Also, we have a special thing here known as sim. So we will bit on that as well. which is actually used to simulate those different physical components like electrical fluids, or like a multi-body is a bit advanced topic for now, but these are the things that can be done here apart from the foundation library. Okay, so inside the foundation library you can find the subgroups as listed here, and you will find related components related to electrical will be found inside these section, and what are the different sensors. Okay, whether we need a voltage sensor and current sensor, or what are the different sources, if it's a voltage source, AC current source, or whatever sources maybe. So those will be found here. Similarly, inside mechanical you will have these subblocks where you can find these things. Okay, and you have to just connect those blocks to make the design. Now coming back to that simple example, so here we have taken a sine wave. So you can see, if I click in this block, I can see this is a sine wave. Also the block name here, and you can click on it, you will get the block here, or else you can go to the library browser, and here, since it is a kind of source, so you have to go to sources and see what kind of sources are available. So there are multiple things available, out of which, suppose this is the sine wave, so I can either drag and drop, or I can also double click or right click and add it to the environment. Right click and add it to here. So these are multiple ways we can add these blocks. So now I have 3 more sine waves which I actually don't require. And once you have this block, you have to double click and see what are different properties and set here. So for instance, a sine wave will have some kind of amplitude and frequency. Also, phase and bias are also there with a sampling time. So as of now, we can see here the amplitude and frequency time is set. We are not providing anything else. So if we don't provide any sample time here, then it will interpret the sample time from the other blocks which are connected. For instance, this is another block known as noise, which is actually a random number generator. So basically, if I type random, then I will get the second one, the random number generator. Okay, so this is one way when you know the name of the block. Okay, so if you don't know the name of the block, then similarly you have to just find out the correct category to it. Like it will be under sources, and under sources you have to find, suppose this is the random generator, so this is the same block. Or if you want to some other block like uniform random generator, you can do that, which will have some differences as mentioned in each of those blocks. So you have to just go to the block and read what kind of thing it performs. So it will output a normally Gaussian distributed random signal, and the output is repeatable for a given seed. Okay, so we have the mean and variance. Whenever we are generating some Gaussian distribution, there will be variance standard deviation. So mean 1, variance 1 is fixed with a sampling time of 0.1. Okay. Next is a add block. So this is a adder block where we have put 2 signals to add. So that it is, we can also make it a subtractor block just by changing the signs here. And now we have this derivative block, so which will do the differentiation. Okay, it's a numerical derivative du dt. So with respect to time, it will derivate the signal. Okay, and we have this integrator block as well. So there are settings associated with it as well. So it will do the integration of that particular signal. So now we have the blocks ready. Or the final block I just didn't mention. This is a scope, like similar to the input portion. Here we want to see the output of the output waveform into some kind of oscilloscope. So that is what this block is doing. So if I double click in this block, you will be able to see. So this is the output waveform window, we can see those, see the waveforms. So there are four windows here, because there are four inputs mentioned here. Now let me connect these blocks. So I'm just connecting the input to the add block, that will add the sinusoidal wave and the noise together, and we will have a resultant wave here. Okay, so maybe I can simply connect the sine wave here, connect the noisy sine wave here. Okay, and send this noisy sine wave to this derivative block, and I want to see the result after derivation, what happens to that noisy sine wave. Similarly, sending it to an integrator, and I want to see the result of the after integration of that sine wave. Connected the block, after which I can use this simulate model icon, which is also the run icon. I'm just simulating it, or I can also type Control T. It will do the same thing. So after simulating, since I simulated it till 100 time stamp, so 100 seconds, so I can see the x-axis from 0 to 100, and these are the four waves. The first one is the sinusoidal wave, okay, and second one noisy sine wave. So after addition of that random number generator, and after differentiation, we see this is the response of the wave, and after integration, the response is something like this. Okay, so this is one way to visualize it, and you can also understand. So those who are in the know about filters, so filters we use those integrators, or the capacitors are used to filter the noise. Similar thing can be observed here. So using the integrator block, we are actually reducing the noise, whereas dy dt, the expression is differentiating this signal so that it will be a even noisier signal. Okay, so these things can be visualized, get started, and you can also put the legend here, which is already put here, but in case you don't have it, you have to just go to the view section and you can put the legends to label them. Now, so do we have any questions still now? Means, or is it okay? Any doubts? Should I proceed with the second demo?
Anand sir. Anand sir.
So just to understand the background of the, yeah. Yes, Professor Simon.
So based on this output, what will be the next steps, actually? We see sine wave and different form, and here we said some integration form. How many times you are doing integration, or what is the relation to it?
Okay, so integration, it is doing it for an so these are the parameters which are mentioned here. So we have provided an initial condition as 0, and we are not using these commands. So these, if you want to keep a saturation limit such as 5 and -5, okay, and suppose I'm doing the same thing now, then so you see, then it will do the integration, but it will have those saturation limits. So when I didn't in the earlier plot, there was no limit to it, so it was integrating as a whole. So as the time was increasing, the overall value was also increasing. If you would have noticed it, let me just show you again. Now there is a different symbol also here. Once I put this limit in that integration, but once I remove it, so it is just the 1 by s operator which is used in that Laplace domain, and now you see it is integrating, but the value is the magnitude is increasing. It is integrating all the signals from which has started over time, starting from 0. So the x-axis is the time axis, and one thing that I didn't mention is so there are multiple solvers behind this Simulink. So how it is solving with respect to time? So this one has chosen this OD45 solver. So if I go here and I open the solver settings, so I can see there are different ways we can select the solver. Either it can be a variable step or a fixed step. So for now we have chosen fixed step, and inside fixed step we have chosen the first command, that is automatic solver selection. So the simulation tool will decide whichever solver is best for the problem. In case it chose OD45 in the background. Okay, there are other solvers as well, but so this setting can also be found from here, which is a very important thing to know. From the modeling section, you have to go to this model setting. Yeah, you can make those changes as well. So does that answer your question, or?
Anand sir, actually, the 1 by s, no, it is a Laplace transform of a function f of t is equal to 1. What is the relation here?
Okay.
Here you have mentioned du by dt for derivative, which means you are doing differentiation of this sine wave, and that corresponding changes is impacted here. And here you are taking Laplace transformation of sine t, but Laplace transformation of sine t is 1 by s square plus 1 actually. What do you mean by 1 by s here? Here actually the function is if f is 1, then this is the corresponding transform. If you take a function sine t, then the corresponding Laplace transform is 1 by s square plus 1.
Okay.
Can you please?
So
what?
Yeah. So
see,
uh,
this 1 by s is the symbol just representing its Laplace transform, or it takes the corresponding Laplace transform of sine t.
So this 1 by s, so that's a this is actually an integrator block, which is denoted with this 1 by s thing. But how do I?
Maybe it may be an integration of sine t. See, as you mentioned, integrated
So
y.
let me.
Yeah. What I think is
Let me explain it in this way. Suppose.
Yes. Yes. Please go ahead, sir.
Yeah. And you're mentioning it right. So inside this continuous block domain, so we have these different mathematical operations that we can perform, right? So one is this derivative and one is this integrator. So I'm actually using this integrator block, so which is also denoted by 1 by s, and usually in Laplace domain we see this any transfer function when it is written in a Laplace in the Laplace domain, we see this term s. So it is actually integrating it with respect to time only, and then we are plotting it with respect to time. So that is being done here.
Okay, sir. Okay, thank you.
Okay, thank you, sir. So now let me go to the second demo. So yeah, let me go to the second demo and demo 2. So now in the second demo, we already have the blocks which we require. So we will be actually going through a RC circuit, and we will try to simulate it using the Simulink blocks, okay, with the mathematical blocks which are available, and also using the physical components like resistor and capacitor available in the Simscape block. Okay, so again we have these blocks which are already taken from the library like pulse generator, and we have a voltage source. So voltage source which is made of this controlled voltage source, and we have a solver configuration. So these are some things which have to be mentioned. We are dealing with Simscape. So I mentioned about Simscape. So whenever we are connecting Simulink and the Simscape block, we need these kind of connectors known as P2S, Simulink to PS converter. So Simulink, let me say, yeah, S to P, yeah, this one. So Simulink to PS converter is one, another is PS to Simulink. Okay, so physical system to Simulink converter and Simulink to physical system converter. So this is what is used here. So this is a Simulink block, and we want to convert it. They're using this. Sorry, let me just zoom it a bit. And yeah, we are using the Simulink to PS converter. Then we are in this block. This is from the physical domain, from the electrical sources, which electrical section that I had shown earlier. And similarly, these are the ports from the Simscape block. So this is a connection that is required. So that you have to just remember important thing. And the other way, the rest of the things are more or less okay. Now, for making the connection, let me just make it quick because we may run out of time. So I will, instead of uh, that, let me just quickly connect it. So I'm connecting this base source to this resistor, okay, and I'm then connecting this resistor to this capacitor, okay, and there is this ground component which is the electrical reference. So even if you are using some other, you will need this reference. So this is important thing, and I want to complete the circuit. So I'm negative port. Here we have these two positive and negative port as you have seen earlier. So we have this positive and negative port which are assigned with these numbers. PMC port, physical modeling connection port, again related to Simscape. So these three blocks are related to Simscape, which will need the solver configuration, and to connect it use convert block with a Simulink port. So this is a normal port, in port Simulink. So this is the details of this voltage source. Okay, I just went inside it, and now I'm back just to show you how we are connecting this Simulink with the physical components. Second, I can connect it to this uh, voltage source, voltage sensor again. So this time we need to sense the voltage. For that we need a kind of sensor which is again a physical component taken from Simscape. Similar manner, we are just connecting, just completing the sensor terminals with the reference as well as the ports with a physical PS2 Simulink blocks to the output port. That's it. So now we can use this sensor and connect it further. Here we are using a MUX. So I will tell you why we are using a mux. So we want to compare the result of the Simscape with the result of Simulink. We have not made the RC circuit using Simulink yet, but we can do it like this, in this manner. So let me just connect it here, and I'm connecting it here, and I'm connecting it here. Okay. Now here we have this transfer function block. Okay. So inside the transfer function, you have to mention the actual transfer function based on the numerator and denominator coefficient. So because this is this RC circuit, so if you just solve V naught by Vi, then you will get numerator will have 1, denominator will have the RC term associated with S. So you have to mention these terms where the first term will correspond to S to the highest power. So here RCS will be the term in the denominator. So you have written RC. Then we do not have any other term. So we have mentioned 0. So that's it. So mentioning that transfer function thing and connecting it to the output port, and again connecting it through the mux to observe both the outputs together. That is the usage of this mux here. We want to see the output together. And apart from the output, we also want to visualize the input. So I'm just connecting it to the input, where this time the input is a pulse generator, which is having a pulse width of 50%, the equal time period, and these are the amplitude and other settings like the time period of pulse and the phase delay. So that's it. So now what I will do is that I will just run this. And I'm opening the scope. So you can see the legend here. The pulse wave is the input, and the output. We have actually two lines. So the first one is output 1, second is output 2. The first one is the result from Simscape, second one is the result from Simulink. So in both we can actually simulate the RC circuit, and you can see we are getting similar result, almost same. And what does the RC circuit do? So it is charging whenever it is getting a higher pulse. When the voltage is reduced, it is discharging again. So charging and discharging based on the charging time, based on the time constant, which depends on the R and C value. So now you must be asking, we didn't define R and C value anywhere, right? So that will actually you need to define it either before running this program in the Matlab window, or again as I mentioned, this modeling part. So here we have this modeling properties where you can go to this collect section and you can mention those Matlab commands like R and C values, R equals to ohm and C equals to 100 microfarad. Okay, so if you mention this, so whenever you are loading the file, so it will automatically run R and C in the background, and it will be loaded here. Otherwise, you will just get an error, and they will ask you to mention the value of R and C. And why R? Because the variable here is named as R. So if you change the name here, then you have to assign it to that particular variable. So that is the thing here. So this is how you can build a particular circuit using Simscape and Simulink in electrical domain. And let me go back to the slide, and let me just briefly do another thing about Simulink. So here, when you are dealing with multiple hardware, so you would be requiring you would need to install some of the support packages related to those hardware devices. Okay, so for that you have to use this add-on section. Okay, so whenever you are working with some hardware, for instance, if you are working with your mobile phone, so you want to connect your Android device and do some kind of experimentation with the Simulink environment, you have to install the support pack for Android device. Okay, from this add-on section, then you can do multiple things. So here you can go through these links to get through these examples to get started. So where we are using the blocks from the Android section in the library. So this is a camera block and this is the display block. So which will read the data from your camera, which is your mobile hardware, and it will just send it again back to the from the Simulink environment. It will again send it back to the display. So here we are not doing any operation. It is a straightforward thing just to test you have installed it correctly. After that, you can do multiple experiments. One such experiment is shown here, where you have made some computation in between. So what is the computation? It is very simple. So this camera which is capturing the video in real time will have red, green, and blue components. Okay, so we are sending those components, and we are also sending a 255 number. So if you know about images, you know images are pictures, so which if convert which vary from 0 to 255 if it is in uint8 format. So we are just subtracting 255 with this value. So this kind of operation will actually invert it. So if you are capturing something of black color, after selection process, you will see it as a white color. Okay. So this operation will take into inside the Simulink environment, and it will then send back to your hardware device. So for that, you have to just select on deploy to hardware. So and you can you will be able to see it. Okay. So let me just show you a quick video of this. So you see these keyboard, this laptop is of the actual color is black, but you are seeing it as a white color. So this is the image inversion thing that you can do at your end also, because this is a very common hardware that everyone has, Android phone. So you can just get started with that before actually doing it with any other hardware that you do not have at this moment. Okay, so this is a good experiment to try. To learn more, you can go through these links where you will have example problems. I'm just opening. Oh, better. It's better. I can uh, copy it in the Control A, Control C, Control A, Control V. Yeah, in the chat window. So getting started with Android devices, you can look over this section and go over the example thing, try it out yourself to see how it works. Okay, at a later stage, but now I will again go back to the slides and so these are different filtering examples which you can do, because your Android device has also sensors apart from your camera. So you have your accelerometer, the gyroscope, so you can capture data, do some filtering process, and see the results as well. So that is where you can make use of Matlab mobile as well in your work. Okay, installing the Matlab mobile app to do certain things along with Simulink. Okay, so we won't. So this is the example that you see in real time, how the data is being captured. Okay, and filtered. So you start with a simple, comfortable with the interface. You can explore multiple cool projects and cool things. Okay, using your mobile and Simulink environment. Now I will now here. Now I will ask Shovik to continue with the presentation. Again, more time as I thought I would, but
Sure.
think,
Yeah, thanks, Anand.
yeah. So I have
Am
to
I
give you
audible?
that presenter privilege, right? Yes, I can hear you. So let me give you the presenter's privilege. Uh, you a presenter. I have made you the presenter now, and
Okay. Yeah, thanks, Anand. Um, I mean, before actually starting up onto this, I'd like to have a little bit of interactions. I mean, I know Professor Simon does a lot of interactions. It's great to always interact with him. But for other people also, if you can, put in the chat window a little bit about how do you think, Simulink can be beneficial for you. First of all, like understanding from Anand. If you have any thoughts, it will be great to know that. And the other part is, I mean, as you can see, many of the Simulink and Simscape, what we have been talking about, this is a little more in the application front, application in the view of engineering front. So if it's like electrical, aero, mechanical, electronics, so whatever be the discipline, and for that specific disciplines, there are multiple things we can do. So on that front, if you can also put your department in the chat window. I mean, we'll share the feedback form and gather that information later on as well. But if some of you can write in the chat window, like which department are you from, so that we can also show you certain things going forward, which can be beneficial for your specific department. So on those fronts, if anybody wants to put any thoughts, like on their thoughts on Simulink, um, and what they would like, what will be beneficial from Simulink from their department perspective. So if you put your department, we can also mention like how it can benefit. So if anybody wants to, put anything in the chat window, that will be really beneficial. You can put either your department, and also like if you think that for something Simulink will be beneficial.
Shovik, sir.
Yes, sir.
Uh, I can see automobile faculty, triple E, mechanical, and
Great.
mathematics.
Okay.
Aeronautical department faculty members are there, and research scholars are there. If you
Okay.
can cover
Sure.
up automobile, aeronautical, it would be great
Everyone.
helpful.
Okay.
And the
Definitely.
triple E, electrical side. It
Okay. Sure.
covers
So
enough.
okay, thank you. Thank you, sir. Yeah, so basically based on that, we'll cover some of those examples, taking basics as well. Um, okay. Um, so let's see, I'll just share the screen as well. Uh, just taking it from what Anand mentioned. So you have seen this platform for now, and you will see a lot more about this platform on Friday as well. This is where we are doing all these things, right? So you've seen in the library browser all this different stuff that comes in, and then in the library browser, what happens is there are all these blocks for different. So you've seen the Android, which Anand talked about. So whatever in this top one here, this top ones are all mathematics related. Now the mathematics can be either core mathematics or mathematics for any department, because maths is there for all departments, right? So all of them are here. So say for example, we can do integrations, first hold transfer functions, and all these things. And this transfer function approach, this is very critical in the controls area. So triple E, mechanical, aero, all of these departments has a lot of different controls focused things. So what we are thinking is we might have something covered on the controls area on Friday. Whenever we are doing the state space representation, this transfer function, so these are all in that area. And then there are things like these type of simple maths operations. These are very like something that we come across maybe like multiple times. So if we have to do products, absolute values, and biases, and things like that. Now once we go down here, of course we can create our own block as well. So you have seen a lot of different things in Matlab. We can basically, if we go to this user defined function, so using these blocks we can create a custom block based on a Matlab code. um, Now, if we go down here gradually, then you will see that there is an aerospace block set. Now, these aerospace block set is primarily for in the area of aerodynamics, right? So it contains both. If say for example, if we have to do an airfoil simulation where we give all these different, so I mean all the blocks operate in the same way, that there are some inputs and some outputs, right? So here basically the aerodynamic forces and moments, these are for the datcom ones. So that is there, and like this it goes on. I mean, of course, as a starting point, going to the aerospace block test is not advisable thing, because it contains a little more complicated and sort of multiple different parameters, and we'll talk about some very simple ones to get started. Now there is audio, automated driving, communication. So once we go down here, you'll see a lot of different things. um, so that's how this is structured. Then we go to robotics, and then at the end there is something called simscape as well. Now if you go to simscape, like what is there, so inside the
Souvik,
foundation lab. Yes, Anand.
Souvik, I just have one question in the chat. So it's a
Sure.
bit advanced question, but I thought just to mention it now. So Professor
Mhm.
is
Yes,
asking how to effectively import CAD models from SolidWorks or other CAD multi-body mechatronics department.
absolutely. Thanks for that question. That is a very valid one. I'll come to that. I'll come
Yeah,
to that in 10
yeah,
15 minutes maybe.
sure,
So yeah,
sure.
now looking into the Simscape Foundation library now, multibody actually will come just after this. So here we see that there are components like this. So there are electrical elements. So if I go inside, electrical capacitor, so all different types of electrical elements. Now these are physical components. These are not mathematical elements. So mathematical means earlier we saw the integrator block, we saw the addition of operation. These are not like that. These are all physical components, and some of these Anand also should talked when he talked about the RLC circuit, right? So that, and then we go to gas, similarly hydraulic, isothermal, liquid. So like this, it goes on. Now how do we do these things? These are very simple. So here we basically don't go to the equation at all. So we basically model the system we want to model. Like what? So if I have to give an example, I mean, aerospace, mechanical, electrical, everybody probably can relate to this. Say, for example, if we have to a model, something like this, a mass spring damper, right? So mass spring damper, it's a very simple. Everybody probably knows it's. I mean, if you have to model this mathematically, it's a second order differential equation. So we can solve. We have talked about all those how to solve ODEs and stuff. So we can use numerical techniques, analytical techniques, and different things to solve the equation. Now, if say for example, if we don't want to go to that route of solving the equation, then what we can do is we can solve the system is a physical way. So now if I search here, like in Simulink, you can search here anything, or you can go to the library browser, and from here, so foundation element, and inside the foundation element, maybe I can go into mechanical, and then inside mechanical translation elements, you can see mass is here. So what I can do is I can just drag this mass here. Uh, right, so mass comes up. Similarly, apart from mass, we can also guess something like a spring. So if I search spring here, then we get a translational spring. And then what we can do is we can also get a damper here. That becomes a translational damper. Now the way we have to connect things here is exactly like the way we connect in the physical world. So what we can do is I'll just rotating this for now. Control R is the shortcut for rotating, and then I connect it. So it's just like the way we draw the free body diagram. So mass, spring, and damper in parallel, and then connected to a reference. So I'm just making it a little bigger so that we can see pretty easily. Maybe I can shake this, and then this is there. So this is there. Now what we need to do is we need to connect this to a reference. So I'll search for a reference. um, it's called mechanical reference, so mechanical translational reference. So if you have like rotational elements, you can do rotational. If you have electrical reference, you can do electrical. So this is about it. Whenever we do things in this way, we need a solver configuration block, because where we can give the solver settings. So that's about it. Now we can solve this problem. I mean, we are ready to solve it. I mean, if I run this, it will run. Um, you'll see that this will, compile, and then it will run. But we won't see any output. The reason we are not seeing any output, again, if you recall what Anand was talking about, so there is the scope block by which we see things, right? So we can get a scope like this. All right, so this is the scope. But if you see here, you won't be able to connect to anywhere. The reason being these are all physical symbols. So these are not now mathematical variables or something. These are physical symbols. So what we need to do is we have to get a sensor here because we need to sense the motion. So what we'll search here is a motion sensor. So this is like an ideal translational motion sensor. Now, if you double click here, you will see the details of the blocks. You will get the source code of it. So this says, like, if you read here, you will see that this R is basically which senses the motion. C is for another motion if we have, like if you have a double mass spring damper. So that way we can have just one more. We can copy paste and create one more. We don't have to solve anything very complicated. So now for now, making things simple, I do not have anything. So I'm just adding a reference here. So this V stands for velocity, P stands for position. So this sensor actually senses so this is like, doing an experiment virtually. So instead of putting physical sensors, we are putting virtual sensors. And this sensor is essentially what the velocity and position ones are. The other thing what we need to do is what again Anand talked about is once we have to convert this physical symbol to a Simulink symbol. So that's why what we are doing, we are just connecting this to the velocity to this converter and then to the scope. So this is for the velocity. Similarly, what we can do is I can get one more of this. So Control C, not this. So maybe I like this, and then I create a copy of it, connect to the position, and then connect to the scope. Right. The other things is, I mean, eventually, if you recall what we do in differential equation is if it's a second order differential equation, we need to give two boundary conditions, rather two initial conditions if it's a time dependent solver. Having said that, one important thing is Simulink is always a time-based solver. So we need to give a time here always. So for this a time-based solver, we are solving for the velocity and position. So what we need to give the initial conditions. So if you go to the spring now, you will see that so this is a spring constant. So and these are also dimensions, right? So in the variables there are the initial velocity and initial position. So here instead of giving that initial condition, we are giving the initial deformation and initial velocity. So here we give the beginning values basically. The mass we can double click, give some values. The damper also you can give some values like whatever we want. So we give the values and that's about it. We can then run this. Um, and once we run this, you can go to the scope and this will give you the plot. Once this scope comes up, so you can see that the plot has there. If I want to solve it for like a more duration, I can give it 100 and then you can run from here as well. So then you will see, this has come up. So this is velocity and position. One of the thing, if you notice here, this is not looking smooth, right? So for that we need to change some of the settings, which we can click here. Also, if you look here, this is like an OD45 being used for solving. OD45 means ordinary differential equation. 45 means fourth order solver with fifth order error. So if I click on this gear looking icon, we can change settings here, like which solver we want to use and things like that. So whether it's a variable solver. So these are, Anand already showed that. So inside the solver details, we can give all these settings. So if I go for fixed step and then maybe reduce the step size, something like this, because I want to make the curve smooth, right? So we need to reduce the step size. So if you do that and then again run this, um, then you can see that this curve has become smoother because we have made the time steps finer. Um, so that's about it. I mean, this is how you can do all this type of simulations. Now, the advantage is if you have like a double mass spring damper, right? What you can do is you can just copy paste this and another one will be created like this. So we don't have to solve too many complicated equations once the system is scaling up. If we have like automobile, right, if you have an entire car, it becomes difficult to have like equations for every part. But if we can do this way, then things become easier. So in the physical modeling approach, um, so like this we can go to a bunch of different things actually. If you look into this library browser, so if I go down here, there is also this aspect of multibody. Since the multibody question came up, inside multibody there are belts and cables, there are body elements, there are different types of joints. So if you're doing a robotics applications or something like that, so these type of joints become very useful. There are different types of gears and couplings as well. So bevel gears, so all these things are there in aerospace, automobile, electrical, mechanical, and so on. So these physical blocks exist. Now it depends on us how we want to connect them to create our system to do something. So now this multi-body part. So I'll just talk about this multi-body part, and then maybe talk about the question. So for the multi-body part, maybe I can just show you, from the example. So if you search here SimScape multi-body, multi-body is basically for multi-body simulations, for physical simulations like robotics. It can be all different type of things. So once we go to SimScape multi-body, you will see that in the examples area there are a bunch of different examples, and these are pretty nice in the form of, this gives like nice visualizations as well. And I'll show a couple of them maybe. So you can see that here we can create a simple pendulums or double pendulums. We can do robots, and um, yeah, this is still loading, but once this comes up, there are all these different type of examples, which works pretty well. I'll probably open up one of them to show how this looks like. um, so say for example, it can start from something very simple and can go into as complicated as we want. So it can go to something like pendulums, to a single link, to more complicated stuff. Say for example, if you have something like this gear or something like this is like a robot, right? So this, if I'll just open this model. This is if there is a robot which needs to be moved in a specific way, specific hand and manipulator, we can use this. Sorry, this not this one. This we just created. This is the one. So if I run this now, you can see how it will come up. It will also show the visual. So it will give the analytics as well as it will give the visualizations. Um, yeah, so this is how it looks like. So we can see the visualization part of it, how the robot is actually drawing this wherever we want it to do the drawing. So this type of visualization also comes up. So this is like one link, there is a revolute joint, there is another link, there is another revolute joint, this sort of things. So similarly, there are a bunch of different type of these things. Once you get started, you will see that there are a lot of different things. There is one on the elevator front, so that's also pretty nice. Maybe I'll try to open up that. Um, so this elevator example is about like modeling an elevator, and it will give you like a belt and pulley mechanism, and that way. Can we do virtuals? And that basically boils down to this question that has been asked, like, can we do virtual simulation of robotic parts and joints? And that's what we were doing here. We can do multiple other things of robotics, inverse kinematics, forward kinematics, simulation of different joints. The advantage is, when you have a robot, and as you mentioned, like if there are joints and then we want to integrate like a motor to it, that also is very much easy to do. Now this one is also sort of a belt and pulley mechanism. It's like simulating an elevator. So this elevator is moving, and you can see this visualizations also come again, where this pulley is moving and this elevator is going. And the resolution of these videos, you can see that people are waiting in the fifth floor and they will come back to the third floor. So that sort of things can also be seen in the visualization. So you'll see here, people coming into the elevator and then they will be dropped in the third floor. So these type of simulations can also be done. So there are all these different type of things which we can do. Now coming back to the question of CAD import, of course for these type of models, we don't recommend doing this drawings in Matlab or Simulink, because this becomes very difficult. If you have any CAD drawing, or if you have any SolidWorks model, we can very easily import that into SimScape multibody. The way to do that, I'll just show you one video. For that, give me 1 second while I pull that up. So basically, once you are in SolidWorks, you need to install a SimScape multibody plugin. And once we have that SimScape multibody plugin, the idea is basically, the thing is, that SimScape multibody plugin will take care of everything. So the way it operates then is, I'll just play this video. So this is, uh, oops, why is this? 1 second somehow. Okay. So this is in the SolidWorks environment, right? So what we can do is once you go to the tools and then there is a SimScape multi-body link and then we click on export, and then what happens is this entire model will be exported in XML format, .xml, and any .xml format. We can basically all these parts will be imported to SimScape multi-body, and once it gets imported to SimScape multi-body, you can basically very easily do any dynamic simulation in SimScape multi-body. Okay, so that is very straightforward to do. So that's something you can do pretty easily. Yeah, does that answer your question, sir? For the CAD modeling part and also the joints part for the robotics application. So I mean, once you get started, there are a bunch of different things. We can share you a lot of different, resources on robot modeling. For robot modeling, we have a lot of, I mean, it starts from integrating a DC motor with the joints, and then if you want to control it via a PID, and like that, and then finally, if you want to deploy it to a hardware, that is also possible very easily, like controlling the hardware through a simulation. So you can change parameters in Simulink and the hardware will change accordingly. So that sort of things also becomes pretty easy to do. And I mean, we have like, full-fledged experience, like demonstrations and slides on robotics, which we can go to, but we are on the top of the hour. But this is how you can get started. And then once you get started, once you do a lot of, we have a lot of courses, and I can pass on to Anand also to talk about those. So once you do those courses, then it becomes easier for, to do about all these more involved problems to do. Any questions apart from that? So like this, we can do a lot of different things, as we can see here in the library browser. So you can use any of these models, and it can go to something like aerodynamics, fluid mechanics, thermals, heat transfer, so all different concepts. So it's a very powerful tool. Industries use it like day in and day out, and they become students who graduate. If they have that skill, it becomes easier for them to get jobs as well. So that's the idea. For different courses in different departments, there are multiple courses which we have created like this. Yeah, any questions, any thoughts?
So there was another question. So it was on
Yes.
want to do fax devices, especially on StatCom from Triple E, professor from Triple E department. So I posted a link on that related to power electronics facts in the chat window. So
Yep.
I
So
hope
that's yeah, power electronics is again, yep. Another big area. So there are a lot of different. So we have a SimScape power electronics. Uh,
I think the fourth
yeah,
example
power SimScape power.
is related to that StatCom. So professor, yeah, yes, you were telling.
Yeah, I was just saying that, yeah, all these blocks are very crucial in the power electronics as well. So um, please feel free to explore them. The link contains a lot of things, so feel free to look into that.
Okay, we have another
Yeah,
question.
Anand. Yep.
So for yeah, so for the basic elements in Simulink, so do we need to download Simulink? If so, can you share links? Okay, so whether we download Simulink or not, that is the question for doing basic experiments. So I would say if you are able to download Simulink, I think it would be the best option, because though you have Simulink online also, it will have some kind of delay depending on the internet speed. So we can definitely, okay, download links is nothing different. It is same. So if you have installed Matlab through your portal, it will contain the Simulink with it is all, it comes all together. Download it quickly. So it's the same.
Yeah, so
You
I
can
mean,
just
it's from the same area only.
post the link to it if, in case you have not. So it is in your website also, I suppose. Professor Simon was mentioning last time. So if you have not created, you have to just create your account, and it has a procedure how you install your MATLAB software. So I would recommend to install it, yeah, because in the browser version it will have some delay due to the internet issues. I am posting everyone again here, and another thing for students, so we have some predefined courses also which could be used as a part of your course, such as Simulink on ramp and Simscape on ramp, and also Stateflow on ramp. There are 3 on ramps. So let me just post those links as well.
Anand, do you want to share the screen and talk about those last part maybe while we wrap up?
Okay, yeah. So yes. So I think again you have to make me the presenter.
Oh, I have to. Okay.
Then I will be able to do that. Yeah.
Yes.
Yeah. Let me share my screen once more, and let me. Yeah, so I was talking about these on ramps. So it is in the same MathWorks Academy website where you can find these. Second one is Simscape on ramp. So after Simulink, if you do Simscape on ramp, then you will get those things which are essential. How you can also connect Simscape block with Simulink, what is solver configuration, and those things. So that would be clear, and it's useful for those who are getting started with this thing to know about these things. Again, let me just post it in the chat window so that you can access it right away. And also we have this Stateflow on RAM. Again, it is in the same environment, where you are actually simulating different state machines. Make a traffic light controller, switching on and off a cooling fan. Some algorithms you just assign certain states and connect it, and you can go through that as well. So these are 3 separate on ramps. So you can use it for your courses, and I hope it will be helpful, and then relate it with the examples which is specific to your courses. For example, if you are in the mechanical department, mass spring damper example, type exam, mechanical example would be more relevant. For the electrical related example would be more relevant. So in that way, you can include it in your courses. So this was uh, this was the this was it from our side. Now we would like you to fill this feedback form. So we have this barcode. Also, we have link. Let me just copy it and link here. So yeah. So if you have any technical related queries, you can always in a mail. So a few of you have asked questions right here. So it is good to know you are working those topics in some advanced areas like Simscape multi-body as well, and in your specific areas. But apart from that, it will be very helpful if you can fill this feedback form. And here also you can mention those questions are again there. What kind of topics you are working, so which will help us in understanding better, and we will try to connect with you. Yeah, we will actually go through the feedback form as well. So this is the feedback form. I just opened it in another window. It's more or less similar. Only thing is this question is to mention whether you're using Simulink for any of your courses or not, and you can specify the course the comment section, you can actually mention those areas. In the same way, some of the professors were mentioning in which course, or even if you are doing research work, what are the topics. Then this will help us in identifying and connecting with you better after the session. So this for the general session for the general audience. So use it or already using it, they find it beneficial. So that's it from the presentation. Now, do we have any more questions? Let me see.
Anand sir. Anand sir.
Yes, sir.
Next week, what are the
Yes,
topics
sir.
we are
Am I
going?
audible?
Yes, sir.
Hello?
You're audible. My question is, what are the topics? What are the topics that you're going to cover to next week, so that if we give some information, they will pass to other members. That will attract more audience. Anand sir, am I audible?
Okay. So next one is on Friday. So yeah, you are audible. So am I audible?
Yes, sir. Yes, sir.
Yes, yes.
Hello?
Anand, I think there is a delay a
Hello?
little bit from your end.
Okay. Okay. Okay, so the next class will be Simulink itself. So Simulink fundamentals is the topic. So I request you to circulate it to every professor who are actually using Simulink or hello, am I audible?
Yeah, now
Hello?
audible, sir.
Okay, now audible. Okay.
Yes, sir.
I don't know. I think the net was. Yeah. So any professor who is interested to learn Simulink or is already using Simulink, so I would request you to tell them. So it will be on Simulink fundamentals. So mainly covering more examples related to it. And meanwhile, I would also request you to go through the on-ramp tutorials shared here. So which are which is a nice way to get started. Actually, it's a 2 hour tutorial. So even if you do not complete it completely, you can get a sense of get the notion of the important points which are mentioned in the initial module, and based on that you can get started with it. So does that answer your question? Hello.
Anand sir.
Oh,
Anand, there is some issue with
was
your
I
internet, it
audible,
seems.
Miss? Yeah. Okay.
Yeah. So can you please spend time next week? Spend time on some mathematical Simulink topics related to mathematics department, because we are the one we are going to introduce Matlab for first year students. If you can cover up some topics related to mathematics toolboxes related to Simulink, it would be a great helpful for us.
Right. So try to interpret some examples which solving those mathematical equations like differentiation, those things. Very much comforting that we can get that. Yeah. So it will be on Friday, this Friday, and we will let you know who is the speaker for it. So it will be mostly from the design tech team.
Okay, sir. Design tech team will handle that section.
Yeah, so Friday's session will be handled by Design Tech, sir.
So
Yeah, I mean, we can probably end the session and, Anand can have a discussion with Simon, sir, later on, because I guess we are not able to hear Anand properly.
You can stop recording, sir. You can stop recording.
Okay.
Sure. And again, please fill up the feedback form for everybody. It'd be great if you can
Yes.
fill up the feedback form.